Hey, Steve, can you hear me? Hey, Steve, can you hear me?
Allison, can you hear me?
Yes, can you hear me okay?
If I can hear you.
Yeah, it says that we blocked your sharing your video. Let me look and see. I don't know why that is the case. I mean, you're a co-host, so it seems like you.
Yes, I should. Maybe I should be able to change it.
How about now? Check now and see if that fixed it.
Okay. Yes.
Perfect.
Online. Let me put a little note on my door. I'll be right back.
Okay, and you're live on YouTube as well, just so you know.
Okay. So I'll try not to do anything too embarrassing.
No worries. I'm sure I've covered it already through all these, so I don't think you can do anything worse than anything I've done. So.
Yeah, recording. So it's one thing to mess up at a seminar or presentation in front of people, but now you can mess up and it will be permanently recorded.
Right. So just so you know, typically, and I'll go back and edit this part out on the YouTube recording of it, but typically we don't have a ton who join live, but then we'll have a fair number who go and watch it later on YouTube. So I'll edit this when we're done on YouTube to clip to the beginning when you actually get started. So it looks like got about a minute before. So we'll give one more minute and then we'll let you. And really, you can just jump right in, introduce yourself, and go from there.
Okay, well, wait a minute.
Yeah. I think you're good to go now.
Okay. All right, let's get started. Thank you guys for coming to this tech talk, which is titled Medicine, Sound Waves, and Magnets. I'll introduce myself first. A little bit about me. My name is Stephen Allen. I'm a assistant research professor in electrical engineering at BYU. I've been here for 3 years and I'm headed kind of straight into my 4th year here at BYU. My background is in physics and biomedical engineering. And I have here a picture of a chimera because at BYU, I kind of have 2 jobs, and I'm going to talk about a little bit about both of them. The first is I manage BYU's magnetic resonance imaging facility. So this is a research dedicated imaging facility. It was founded in 2012. And our mission is to try to get as many students as possible to have really cool experiences conducting research with this machine. So we have students come who study injury recovery in dancers and football players. We have other students who come and use the machine to study brain activity during sleep. We have studies investigating diabetes, back pain, muscle soreness after exercise, ACL repair. It's a pretty wide variety. We have people coming from the School of Business, the Department of Dance, Exercise Science, Physics, Engineering. Really, the only departments that I have yet to get to participate at this facility are University Administration and Art and Music and Music Theater. So those are kind of my next people I want to get involved at this facility. And I'm just going to show a really cool time-lapse video. So this was founded in 2012, and our MRI scanner we bought used, it was constructed in 2004. There it is coming out, and we replaced it with a brand new one. So BYU administration was really generous, and they also kind of caught the vision of what we're trying to do, and they helped us get a new MRI scanner so we can keep doing this for years to come. So the old scanner was about 28,000 pounds, and it had a special forklift. And the new scanner, you can see it being installed right there, weighs 17,000 pounds. So it's a little bit lighter. And so that is up and running, and we are operational. Okay, so that's one of my jobs at BYU. The second one is a standard professor. So I teach courses, and I also conduct research. And I'm happy to talk about the research that my lab does with you guys right now. So I'm going to talk about 3 diseases of interest. So these are human diseases that my research and my lab, we are trying to use our engineering skills to try to come up with better ways to understand and treat these diseases. So I'll be discussing mental health, essential tremor, and pediatric brain tumors. So let's first talk about mental health. This is becoming a more common topic of discussion. Mental health affects mental health issues such as depression, anxiety, compulsion, obsession. They affect approximately 1 in 5 adults. We seem to both have greater awareness of these issues, and they seem to be more prevalent nowadays. One of the issues with treating these diseases, mental health disorders, are both a lack of effective treatments and also a poor biological understanding of what our brains are actually doing when we suffer from these diseases. So my lab is interested in a potential tool to both treat and understand mental health disorders, and it's called focused ultrasound. I have here a little diagram on the right-hand side of what we hope focused ultrasound neuromodulation can do, which is you have like a single applicator or a phased array applicator or emitter that emits acoustic waves at ultrasonic frequencies, so roughly 200 kilohertz or above. And these acoustic waves propagate through the intact skin and skull, and propagate down toward a focus somewhere inside the brain. So this focus is small, it's spatially localized, it's also transient in time, and if you build your array of transducers correctly, you can kind of focus the sound to most locations in the brain. We can also do this at low power and cause reversible effects in the brain. So hopefully what you can see is a potentially really nice tool to use ultrasound to kind of poke and prod the brain and see what happens, and also as a therapeutic tool to kind of modify the brain of somebody who's perhaps suffering from some of these diseases, and hopefully help them live a better life, have better symptoms, or kind of stop some of the symptoms of their disease. So I didn't invent this. There are many researchers in the field. investigators, and I just want to cover some of the results that they've found. So this is a lab that has found that focused ultrasound modulates the activity of the primary somatosensory cortex in humans. That's really exciting. Focused ultrasound can kind of modulate activity. But then there's another group that says, well, wait a second, we found that focused ultrasound suppresses action potentials in rat brain. So they don't modify the firing rates that we observe in the brain. They just suppress brain activity. And then here's another group that says, well, actually what we found is that ultrasound, focused ultrasound, doesn't stimulate or modify brain activity, and it also doesn't suppress brain activity, but it seems to create a more fertile ground so that if you have some kind of stimulus for the brain, it becomes easier to stimulate the brain. And then finally, here's another group in the field that says, well, wait a second, no. Focused ultrasound does activate the brain, but it doesn't do so directly. You just simply have sound conducting through the bones, the skull bone, into the ear, and you're just activating the auditory pathways of the brain. So hopefully what you can see is that in this field of research, it's kind of a jungle out there. There's lots of different contradictory results. People seem to have inconsistent results from their experiments. And why might this be? So one reason is, of course, that the brain is inherently complex. So if you shoot sound in one spot, you may get a different response because the brain is just really complicated. But another important reason is that for all of these experiments that I've shown you, all of these results, the actual acoustic field that's being deposited into the subject is unknown. And the reason for that is that human skulls and animal skulls are acoustically attenuating and acoustically aberrating. So when you send in an ultrasound wave, it gets warped. And like a fingerprint, every human skull is unique. So for every experiment you do, the ultrasound field undergoes a unique attenuating and warping procedure or operation. And so for this reason, if we don't have an actual measurement of the acoustic field, we have imperfect control over our experimental parameters. And there is no known way so far to measure the acoustic field in a living subject without inserting a probe into their brain. So what my lab is trying to do is develop a remote hydrophone using magnetic resonance imaging. So basically, if you have an acoustic wave that's simulated here on the left, a longitudinal pressure wave, we want to produce something here like what's here on the right-hand side, which is a quantitative measure of an acoustic wave propagating through something. And this image is taken using a magnetic resonance imaging device. So the idea that I'm proposing to you is not entirely new. In the 90s, there was a group in Toronto by the last name of Plews and Walker, who built this custom device. It's a Maxwell pair electromagnetic coil with a ultrasound device and a gel that can conduct acoustic waves. They built this device and they were able to produce the image that's up here on the right-hand side. It's a pretty amazing achievement. There are some practical reasons why development of that device and its translation into humans stopped. So I have here on the right-hand side kind of a schematic of the Plews and Walker device. You've got these two red coils that represent a Maxwell pair, electromagnet, and this kind of orange fuzzy region is the region over which this device can sensitize MR images to acoustic propagation. And finally, this TX means transducer, and it kind of indicates acoustic waves as they propagate into this region of sensitivity. Now, hopefully what you can see is these small pair of coils with their region of sensitivity. It's quite difficult to place a human head or the brain that you want to examine inside this device. It's too small. It also consumes a considerable amount of power, 175 watts of power. It's not quite ready for translation into human use. So our idea is to remove one of the coils. Instead of having a pair of coils in this electromagnet design, let's just use one coil. There's advantages and disadvantages with this design choice. Advantages include greatly reduced power consumption, a smaller form factor that is then, as you can see on the right-hand side, compatible with human use. And because it's more efficient, you can produce very large magnetic fields, which we want to do. The trade-off is that the magnetic field produced by this single coil is less focused, less linear, and a little more difficult to deal with mathematically. But we feel like that is a trade-off that we can deal with. So my student, David Cavinato, who's shown on the upper right-hand side, he's kind of designed the driving system for this coil. He's built the coil. We've been able to take magnetic field measurements off the coil, and they fit the specifications that we need them to do. The whole setup has about 0.3 ohms of resistance. So we have to have a transformer to match the impedance. We can drive about 12 amps of current through this device, which produces the magnetic field that we need. And at least here's like a little a 3D picture of how we envision this device will work. We found that it consumes 23 watts of power as opposed to 175 watts of power. It also doesn't heat up or undergo Lorentz forces when it's in the MRI scanner. So the coil works great. My other student, Carson Reed, he is building the missing piece, which is the ultrasound applicator. So here's a little picture of a prototype ultrasound applicator that he built to generate the acoustic field. We also need to quantify it in a water tank using hydrophones so we can compare the water tank measurements to what we observe with the MRI scanner and confirm the accuracy of the MRI scanner. So our hope is that we can create this device that can do neuromodulation, but also have the acoustic field that does the neuromodulation be remotely quantified and characterized for each subject that undergoes an experiment. And we have a lot more work to do, especially we need to drive more electric current and produce even stronger magnetic fields if we want to visualize acoustic fields deeper in the brain. Okay, so that is a summary of our work for mental health and focused ultrasound neuromodulation. The next disease that I'd like to talk about is a disease called essential tremor. Essential tremor is a movement disorder. What that means, it affects about 10% of the population, and it particularly affects older population. What I mean by movement disorder is that people with this disease, if they try to drink a glass of water or button their shirt or shake your hand, or in the case of this picture, if they try to draw a pencil between the two lines of this spiral pattern, their hands start to shake uncontrollably. And the disease can progress to the point where you can no longer feed yourself, you can no longer dress yourself. People tend to socially withdraw when they have this disease because they can't wave hello, they can't shake your hand. And what we'd like to do is restore a patient's control over their hands so that if they were to draw the circle here on the right-hand side, they can maintain enough control to keep the pencil within the two lines. So hopefully you can see that essential tremor, while not deadly, does represent a severe loss in quality of life. It turns out ultrasound can be used to diminish the symptoms experienced in essential tremor. The way that we've managed to be able to do this is we have a hemispherical shell full of about 1,024 individual ultrasound applicators. They all produce an acoustic beam that propagates through this blue water coupling bath. The red lines represent the acoustic beams. The ultrasound waves propagate through the intact skin, the intact skull, and then focus down to a single point about the size of a grain of rice. And if we've placed that grain of rice in the right spot in the brain, it will heat up, it'll absorb energy and heat up and eventually ablate or kind of cook the neurons that are associated with this shaking pattern. And if we just burn that right spot, then afterward, the subject's shaking disappears, and they're able to feed themselves, they're able to drink water, clothe themselves. They have this kind of miraculous recovery simply because we've cooked this tiny little spot right in the middle of the brain. Now, I can probably tell what you're thinking, which in my case, I would be thinking, well, I hope that surgeon places that grain of rice in the right spot. And to help surgeons do that, we do this whole procedure with the ultrasound in a magnetic resonance imaging scanner. And the magnetic resonance imaging scanner can monitor the temperatures that are induced by this treatment and can make sure that that grain of rice is at the right spot in the brain. The target is called the venturo-intermediate nucleus of the thalamus in the brain. Now, you may think, okay, that's pretty cool. I know somebody who could benefit from this treatment. But the sad fact is not everybody is a good candidate for this sort of treatment. And the reason is for the exact same reason I described above, which is that every skull is unique. And some people have skulls that are incompatible with treatment. What I mean by incompatible with treatment is represented by this picture right here. On the right-hand side, we have this thick skull that nicely conducts ultrasound. This is a good candidate skull. On the left-hand side, this skull has a really thick section of marrow in the skull, and marrow is highly absorbing for ultrasound. So as the acoustic beams propagate through the skull, they get absorbed, and the marrow heats up. And eventually the marrow in the skull may heat up so much that it may start to damage the surface of the brain that's right up against the skull. So for this reason, if you go to get a focused ultrasound treatment for essential tremor, you will first get a CT scan of your skull, and your surgeon will look at your skull and they might say, I'm sorry, but we can't treat you because the risk of heating up your skull and damaging the surface of your brain is too great. You'll have to find some other treatment method. Before I get to that point, I just want to point out that one way to reduce this problem is to use this blue acoustic coupling bath as a heat sink. So it's chilled to about 50 degrees Fahrenheit. It's pretty cold. And it's able to wick away heat from the skull. This water bath is kept static. It's not circulated, although it would be vastly more efficient as a heat sink if we were able to circulate it. The reason why we can't circulate the water is because moving water destroys the MRI images. So I have here some examples of MR images. The red arrows point to different ways that the water bath there, that heat sink water bath, disrupts the ability of the images to work their magic. And as I said before, we rely on imaging to make sure that the grain of rice is at the right location in the brain. So we cannot tolerate anything that will disrupt the quality of the MR images, and we therefore cannot circulate the water. But if we could circulate water, it would be a much more efficient heat sink, and it would allow a larger population of patients to enjoy the benefits of this treatment. So this is where my lab comes in. Our hypothesis is maybe we could replace this water with something that is both invisible to the MRI scanner, but it's still able to act as a heat sink and wick heat away from the skull during these treatments. So one of my collaborators, Dr. Rick Davis at Virginia Tech, has helped us invent this fluid. He basically creates these iron oxide particles with a really special coating on them. And if we sprinkle these particles into the water bath, it turns an image like here on the right-hand side where you have this bright water bath that's moving and causing all kinds of fuzziness in this gel target this gel is pretending to be a human head. And if we just sprinkle some of these particles at about a 3.1 millimolar concentration into the water bath, then even though the water bath is present and it's moving around and circulating, all of those imaging problems just kind of disappear because those particles render the water bath invisible to the MRI scanner. And so our goal and hope is that we can use these particles to allow continuous water circulation during these treatments, which will efficiently cool the skull, allow surgeons to transmit more energy into patients with highly attenuative skulls. So there's some like technical results, which we've been able to show that the precision and accuracy of the MRI scanner improves when we use this nanofluid. And we also have qualitative data that show when we use water on the left, we have like fuzziness in this image. And sometimes we have these aliasing patterns that you can see on the top and bottom of the image. And then if we just simply replace the fluid and take identical pictures, here on the right-hand side, a lot of the errors in the image go away. We have improved contrast to noise as indicated by these blue arrows. This project is really fun because it's a balance between so many physical properties. There's acoustic properties such as impedance and attenuation, likelihood of cavitation, mechanical properties such as viscosity and thermal conductivity. There's magnetic resonance imaging properties such as relaxivity, signal to noise, contrast, resolution. And then there's chemical nanoparticle properties such as stability, opacity, and toxicity. And all of these properties all have to kind of be in balance with each other as we design these fluids. So there's a lot more work to be done. We want to optimize these particles, optimize the fluid properties, quantify the benefits of using this fluid as opposed to just water. And also, is there a way we can optimize the fluid flow states to maximize cooling in the skull and allow more patients to benefit from the surgery? Okay, we are on to the last disease that I want to talk about, which is pediatric brain tumors. So we also have a pediatric brain tumor project in my lab. So pediatric brain tumors are a minority of the total brain tumor population. About 4,300 children are diagnosed every year in the United States. These children have a 30% survival rate. 30% survival rate is not great. But it is far, far better than it used to be. One of the major problems with pediatric patients is when they survive, they oftentimes suffer from what are called late effects. Late effects is this kind of euphemistic term that refers to the long-term consequences of chemotherapy, tumor resection, and radiation treatment. So if you're a 60, 70-year-old person and you undergo chemotherapy, you're not really worried about the effects of chemotherapy on your body 30 years down the road. But we hope that our pediatric population, we hope that they'll live for 60, 70 years. And the effects of radiation and chemotherapy kind of can be kind of difficult to live with over that long period of time. I mean, you have toxicity issues, you're at a much higher likelihood of cardiac problems when you undergo chemotherapy. Radiation treatments can destroy a tumor, but it can also increase the likelihood of getting more tumors in the future. You know, these late effects cause a lot of problems for the pediatric population. They cause a lot of problems for kids. So my lab, we are investigating a treatment called histotripsy. This is once again a focused ultrasound treatment where we have an array of acoustic applicators that propagate sound through the skull into the brain. Except this time, we modify the wave patterns, the acoustic wave patterns, so that instead of depositing heat, the acoustic waves kind of fracture apart the water that's inside tissue, and they produce these really transient and violent cavities of bubbles. We call it cavitation. It's ultrasound triggered. You have to use dedicated hardware to cause these bubbles to form. The bubbles in their local environment are incredibly violent. They're also transient in time. Here on the right-hand side is an example of liver cells who have been exposed to these bubbles. So untreated liver cells on the upper right-hand side, they look normal, they look happy and healthy, they have a lot of structure. But cells that have been exposed to these bubbles are just completely emulsified. They're completely destroyed. And so our hope is that this treatment, if we were to expose pediatric tumor cells to these bubbles, then the tumors would be destroyed. Now, because it's an ultrasound treatment, it's non-ionizing, so you don't have the late effects associated with radiation. It's also non-toxic, so you avoid late effects associated with chemotherapy. And it's non-invasive, so you can avoid some of the late effects associated with surgery. So we think this could really benefit the pediatric tumor population. Now, histotripsy is really cool, but everybody who's able to do it does it with really specialized, expensive, difficult to manufacture ultrasound transducers. Using new devices is taking a new device through the entire regulatory pathway into clinical use is incredibly hard. And it would be way faster, more efficient and more cost effective and easier from a hospital business model sense if we could do histotripsy using these clinical focused ultrasound transducers that we use for essential tremor. This would be really great. A lot of people have been very interested in doing this kind of conversion, but most people have agreed that it's impossible. So this paper here is like a theoretical paper that says all the theory says that we shouldn't be able to do histotripsy cavitation using these existing clinical devices. But meanwhile, my colleague, Dr. Henry Godin at the University of Utah, seems to have found a particular kind of incantation of acoustic pulsing parameters that produces histotripsy-like effects in tissue samples. They seem to produce bubbles that emulsify tissue rather than thermally ablating tissue. And we don't know why. It seems like the field has a consensus, other researchers have a consensus that this should be sort of impossible to do using this clinical device, but we seem to be able to produce results that counteract all of their claims, and we're not sure why. So Dr. Odin and I have created what we call our matrix of hypotheses, which is where, like, this isn't even the whole matrix, it's this huge spreadsheet. Where every column represents a hypothesis for what's going on. And then every row represents an experiment that we could try using this device, and the results that would then be predicted by each hypothesis. And so what we've had to do is create enough observations so that each hypothesis has like a unique pattern of observations. And so if we just kind of run through all of these experiments, we hope to be able to identify what is the mechanism that's causing histotripsy using this transducer, and how can we optimize it so that we can treat pediatric brain tumors, or eventually, translate it into pediatric brain tumor treatments. So my student, Libby Allen, up here on the right-hand side, is helping construct ultrasound targets. They're made out of gels. that with tunable acoustic attenuation properties, tunable mechanical stiffness properties. And also they produce in MR images some nice bright contrast when we shoot them with ultrasound, so we can see where we're shooting and how effective we are at treating. And these gels are kind of key to that row of experiments that I described above. So I think I've gone on for about 30 minutes. We have other projects and there's other people using the MRI facility. There's just too much to talk about. So I want to thank everybody for your time at this Tech Talk. And I also have to thank all of my students here at BYU and collaborators at other places and funding sources. And I think now we can transition into question time. So let me see.
I think we
have any.
We don't have any questions right now. I've been watching the chat too, so I think we can wrap this up.
Okay.
This has been fascinating to me. I have some questions for you afterwards.
Okay.
I'll catch you next week. So
yeah. So biomedical engineering is fantastic because there's like no area of engineering or physics that's untouched. You have to use all of it to try to treat the human body. So it's really fun.
I believe it. My son is a PA and he got his undergrad in neuroscience and did some work in the MRI lab too.
Oh, he did?
I was actually just texting him and I said, I know you're working right now, but I'm going to give you the link because I know he's going to want to watch this afterwards. So yeah, this is fascinating. Yeah, this is good stuff. So, well, thank you. I think we will close for now. And appreciate you doing this and look forward to the next one. So Thank you so much. Appreciate it, Dr. Allen.
Yeah, you're welcome. Thank you for your time and attention as well.
All right. Have a great day.